Okay. Okay, fantastic. Alright, cool. I'm going to give Dylan my phone so that he'll sort of just communicate with. Okay, this is now the real stuff. Okay, again, hi guys, my name is Ernest. As I was saying about this workshop, we're going to go through several sections, right, covering the grade 11 syllabus. So we're going to first go through some physics, then some chemistry with a break in between. So then, like I said, we're going to start off basically covering some content, teaching for about 10, 15 minutes, do a nice worked example, and then we'll do some work, and practice. Okay? As I said before, I'm here, Dylan's there, Robin's there in the back. And if you have any questions, any queries, while I'm presenting, put your hand up and I'll answer your question. If you have a question while you're doing the work, just ask Dylan or Robin or myself, and we'll come there and sort you guys out. Cool. Just one thing that I want you guys to just a nice big scream, hello, welcome. Colin on the other end in Cape Town. So just on 3, just say, welcome, Excel Cape Town. Okay. 1, 2, 3.
Welcome, Excel Cape Town.
Okay, just a bit more enthusiastic. Okay. 1, 2, 3.
Welcome, Excel Cape Town.
Okay, that's better. Sweet. So now, as we get started, I'm going to say my rules again. Rule number 1, please ask lots of questions. Okay? Rule number 2, what was rule number 2, Gemma? Gemma forgot rule number 2. Okay, remember, ask lots and lots of questions. Okay? With me in the front, with everyone out there, that's all I want you guys to do. You can't gain more knowledge unless you ask. Okay? Okay, and then what we're going to do now is we're going to start off with some vectors. If you guys turn to page 1, not 1, 4, you'll find it says physics, forces, and Newton's laws. Okay? Now, by a show of hands, who's like more than 60% confident with this section, with vectors and Newton's laws? Okay, who's more than 50% confident about this section? About half the class. Who's more than 40% confident? Okay, I'm going to get down all the way to the bottom. Who's like, I have no idea what's going on with this section? Okay, cool. So now, if we look now at our physics forces and Newton's laws, we have our definitions there, right? About the normal force, a frictional force, and static frictional force, and so on. Okay. So now, the key thing about this section, guys, is that if you guys remember, you guys are all in matric now. We're doing this so that we can prepare you guys to actually finish the matric syllabus really well. And a lot of the foundation is done in grade 11. So when you get into like work, energy, and power, momentum, that needs a lot of knowledge from grade 11 and grade 10, motion and vectors and forces and newtons. Okay? So as you're going to see me going through this now, the key topics to know, make sure you know what a vector is. Make sure you know how to draw a vector. Make sure you know how to draw a vector diagram, how to draw a free body diagram, how to draw a force diagram. Okay? So now if you look at the top of your page, it says a normal force, that's the force, right, or the component of a force which a surface exerts on an object which is in contact and which is perpendicular to the surface. So if you look at any object resting on a surface, so if me standing here right now, I'm exerting a force onto the floor, and the floor is exerting a force right back onto me. Right? Which one of Newton's laws states that? Newton's third law, yes. Okay. So now, whenever I'm resting on a surface, in this case the floor will exert a force back up onto me. Yeah? So if I decide to lean on the board, that's again me resting on a surface. That surface will exert a force back onto me, correct? Okay, fantastic. So now, let's start with just the basics of what a vector is. What is a vector? It's a... Michael? Okay, cool. So a vector is a physical quantity, right? What's a physical quantity? Something that you can measure. So the distance between me and the laptop, that's a measurable distance. The distance between me and the ceiling, measurable distance. How hot is it? We can actually measure how hot it is. Anything that you can physically measure is a physical quantity. So now a vector is a physical quantity with both magnitude and direction. Very important. Okay? So now, let's put this down here. And direction. Cool, so let's look at now, well, if it isn't a vector, what would it be then? Come again?
Scalar.
Yeah, a scalar. So if it isn't a vector, it's a scalar. And a scalar is simply a physical quantity with only a magnitude, no direction at all. So then how do you decide, is it a vector or is it a scalar? So normally what I do in the test is, does it sound weird when I say it? So then I think, well, I'm going to walk 5 meters in the direction of the window. Okay, that's a direction to my distance, or my rather displacement in this case. But if I were to say, ooh, today feels quite warm, like 40 degrees Celsius upwards, doesn't sound too awesome. Or my mass is 10 kilograms that way, that doesn't sound too awesome. Okay, so just remember, take the magnitude with the direction, and if it sounds okay, it usually is a vector. So normally what I say is learn all your vectors, learn all your scalars. Okay, representing a vector graphically, we use the arrow with an arrowhead, and our arrow length represents
Strength.
magnitude. Yeah, so this is our magnitude. Right? And the arrowhead represents the direction. Okay, fantastic. So now when we're going to add vectors, we're going to start off with our vectors in one dimension, just purely in a single direction, either this way or that way, or either this way or that way. Okay, so now what I'm going to introduce now is the concept of picking a sign convention. So a sign convention is simply saying, if anything acts to the right, I'll call that positive. If anything acts to the left, I'll call that negative. Because remember, with vectors, you don't just add them sort of algebraically, right? So if anything to the left is negative, left, that's going to be negative 10 newtons. Makes sense, right? Okay, if we look at the example there, we've got now a vector acting to the left, F1 being 10 newtons, and we've got another vector acting to the right, F2 being 15 newtons. Yes? So then we're going to get now what we call our resultant vector. What's a resultant vector? Anyone?
The net vector.
Okay, it's a net vector, but if I had to give a definition now, it's a single vector that has the same effect as a system of other vectors working together on an object. Yeah? So now, so imagine now I had a sort of strong guy like Dylan pushing me or a table this way with like 10 newtons of force. And you get an even stronger guy pushing the table that way with 15 newtons of force. What'll generally happen? Let's work it out. So we say F net is equal to now my F1 plus my F2. In this case, my F1 is acting now to the left with 10 newtons, that's going to be negative 10, plus my F2 is acting that way with 15, that's a plus 15. We end up with plus 5 newtons. The nice thing about this is, the final answer, the sign will tell you exactly what direction your vector is acting. So even if you didn't know where your resultant would end up being, look at your final sign, it'll tell you exactly where your resultant is. So if you, I know like some people like saying, you'll just say F2 minus F1. And if you assume that wrong, you're going to get your final answer just telling you negative, meaning actually it was in the other direction, not the one that you originally assumed. Make sense? Does it make sense?
Yes.
That's rule 2, remember? I like feedback. Cool. Now, if you guys turn the page over, we can look at vectors in 2 dimensions.
Sorry, can I just ask?
Yep.
If you came out with a negative sign and you just said in the opposite direction and you didn't say left or right, would that be okay?
The opposite thing is you have to give an absolute direction.
Okay.
Saying the opposite direction, there's no reference point to that. So if I said, hey, I'm walking, you're like, well, walk in the opposite direction. You don't even know where I was walking initially, so the opposite doesn't tell you exactly where you are. So if you say opposite direction to the original motion, that makes sense. Okay.
But if the question says like the object is travelling to the right, calculate the net force, whatever,
Yeah.
like a change in it, and
Yeah.
then it's travelling to the left and you get a negative, can you say in the opposite direction and it will apply?
Well, you have to specify to the original motion.
Okay.
Yeah. Cool. So now we're going to look at vectors in 2 dimensions very quickly. So when we now, so that was plain, simple, basic, grade 10 stuff. Yes?
Yeah.
So now let's go upper dimension. So now we're looking at what if the vectors aren't acting in a straight line? What if one guy's pushing this way and the other guy's pushing perpendicular to it? Okay? Well, in that case, let's now imagine we have one guy pushing upwards at like 5 newtons, for example, right? And another guy is pushing now perpendicular to the first guy at also, let's say, 5 newtons of force. This is where now our vector diagrams become very important, okay? Who knows by show of hands how to draw a vector diagram? 1, 2, 3, 4, 5. Okay, that's fine. Cool. So with the vector diagram, what we need to do is we need to start by drawing our vectors all from head to tail. Yes? So then This is now called your triangle method of adding vectors. So I'm gonna leave the 5 Newton one as is there, and all I'll do is I'll shift the 5 Newton one. I can shift it down here, or I can shift it up here. Either way, you end up with the same triangle. Okay, that's 5 newtons here. That one comes down there, also 5 newtons. We end up with a right angle triangle if we complete it like this. So then the key thing to remember here is when you do this, your resultant vector will always be from the tail of your first vector to the head of your last vector. You can do this with any number of vectors. If I gave you 15 vectors, I'm only going to draw 3 of them, or like 4 of them. So if I gave you a vector this way, a vector that way, a vector this way, and a vector that way, your resultant will just be from here all the way in a straight line to there. Make sense? Any questions? No? Cool. So now continuing from here, we've got a right angle triangle. How do we work out the hypotenuse of a right angle triangle? Pythag. Sweet. So Pythagoras, we find that. Okay, cool. I'm going to call this now my f in the x direction. I'm going to call this my f in the y direction. Is that okay with everyone? Cool. Pythag, then my hypotenuse or my resultant squared is equal to my fx squared plus my fy squared. Everyone happy? Okay. Then substitute, I'm going to end up with 5 squared plus 5 squared, and that's going to give me 25, that's still r squared, that's still r squared. That gives me 25 plus 25, and then r will simply be, if I square root both sides, r will be, can anyone give me an answer quickly? Of square root of 50? Seven point?
1.
Okay. 7.1 newtons. In what direction will that be? Anyone?
Positive direction. Right.
Yeah? Yeah, you have to find the direction. No, okay. You have to find the direction, right? So obviously it's not going to be now up, down, left, or right. That's now acting at an angle. So if you look at this triangle, if I call this angle here theta, we can find now the angle theta. So then in this case, this is still a triangle, right angle triangle. I can use my trig identities or my trig ratios. So I can obviously see, okay, if I go tan, I get 5 divided by 5. I can use sine, I can use cos. The reason I won't try use sine or cos is that sine or cos would require me to use my resultant. And if I got this wrong, I will definitely get the angle wrong as well. So I'm going to try use the values that they gave me instead of the ones that I worked out. So let's get the angle there. So if we see tan theta is equal to opposite over adjacent, so that's easy. So I can say my inverse tan, right, of my opposite over my adjacent will give me the angle theta that I'm looking for, correct? Okay, and then I simply say theta is equal to my inverse tan of 5 divided by 5, which is basically 1. What's the inverse tan of 1? Putting some maths back in. 45 degrees, perfect. Is that the final answer?
No.
No, why?
It's not relative.
Yeah, it's not, there's no reference point. So then you can then say at that point, either it's going to be 45 degrees clockwise from my x vector. You can say it's 45 degrees north of west. I personally like using bearings. So you know bearings, you start at your north and you go clockwise all the way around until you find the actual angle. So if I use a bearing, it'll be 0, 90, 180, 270, plus 45, which will give us 315 degrees. Well done. So then we can say 315 degrees bearing. Is that easy enough?
Yep.
Okay, cool. So now, the next thing we're going to cover quite quickly as well are components of vectors as well as vectors in equilibrium. Just to double check, everyone is with me until this very point.
Yes.
Okay, and if I say you're with me, you must be 100% with me. If you're 95% sure thinking, yeah, as he carries on I'll catch up, that probably will not happen. So if you're 100% sure right now, say yes I am.
Yes, I am.
Okay, cool, thank you. So now let's look at vector. Sorry, yeah?
How do you know which angle to use?
You can use any angle, so long as your final answer, you can give it like relative to a proper reference point. So if I had let's say a vector this way, okay, you can use that alpha there. So let's say this is like my north, that's my west, and this is theta, right? You can use any angle whatsoever. So if I use this angle here, I can then say it's going to be alpha degrees west of north. If I use the bottom angle here, it'll be theta degrees north of west. Or if I want to use bearing, it'll be 360 minus alpha to that bearing there. And then you can even say, if these two are the same, that's going to be purely northwest. Yeah, so any sort of one of the ways you have to describe any direction, use them. As long as you have a definite reference point, it'll work. Cool. Okay, so now dealing with components. So I want you guys to sort of think back to like grade 4, or grade 3, or even grade 5 maths, when you sort of started learning how to add stuff and sort of minus things. Okay, if I say 4 plus 3, what does that give me? 7. If I say 5 plus 2, what does that give me?
7.
Okay, if I say 6 plus 1, what does that give me? 7. If I say 7 plus 0, what does that give me?
7.
Okay, fine. Notice how there's lots of ways to take different numbers and add 7. We can call these components of the number 7. Yes? So if I add all these numbers, I'll always get 7. So just like when you're adding vectors, you can add a big variety of vectors, and you could end up with the same resultant. True? Okay. Now, with components is basically going from the answer to vectors that will add up to that resultant. Does anyone know why we actually do this? Does anyone know why we do this?
So
So we can work?
in one place.
Yeah, exactly. See, like as we started, I showed you guys that we can normally only add, right, algebraically vectors that are in the same direction. So what we do with vectors that are now, if there's one vector this way and like one vector that way, we don't really know how to add them unless they're at 90 degrees. And then if they're not, let's say this was 100 degrees, we wouldn't really know how to add them. But if we can resolve each of these vectors into a component that's purely up and purely right or left or down, then we know we're working in two planes. So just this one and that direction there. Meaning I can add up all the y components, I can add up all the x components because they're all in the same direction. And then at the end, I end up with two perpendicular vectors, which we know how to add because we just did Pythagoras right now to get our resultant, and that's that. So the key thing now is we're going to try and find the components that end up sort of adding up quite nicely. So it's like if I said, find the two components of 7 that are less than 5, right? Because let's say you want to work with very small numbers. You'd end up using these ones. Two components of 7 that are more than 5, well, it doesn't have any, and you can't really solve that one. Okay, so now let's look at vector components. Now I'm going to draw that triangle again. So let's say this is our resultant vector. Okay, I can break this resultant vector up. So if I did this, again my triangle method, so you can clearly see that if I add this vector and that vector, I get my resultant. True? So I'm going to pick two components that are at right angles to each other. So now if I've got this triangle, and I've got like an angle theta here, I find these two I'm going to get opposite over hypotenuse, right? So let's call this our y component of the resultant. Let's call this our x component of the resultant. So if I say sine theta, I end up with opposite over my hypotenuse. And if I write that in terms of my opposite, I get, so let me show you now. So we have sine theta equals our opposite over our hypotenuse. That's going to be our fy divided by our resultant, and that's for sine theta. And if I solve for my fy, you find that if I multiply both sides by r, fy is equal to my resultant times sine theta. And that will always work, provided theta is the angle between your x-axis and your vector. Okay, if the theta was there, it wouldn't work. You'd have to find this theta and then use that equation, or look at your diagram like sideways and then use that theta. But then in that case, now your vertical becomes cos and your horizontal becomes sine. So in this case, what I always find easy is just find this angle. Once you've got this angle, this equation will always work. And you can do the same proof to find the x one, and you'll see that now cos theta is adjacent over hypotenuse, and if you do the same method, you find that your x component will always be equal to the actual vector times cos of theta. Does that make sense? Okay, cool. So now, what I want you guys to do is to turn to page 8 in your books. Give me a quick yay when you're there. No one in the back is there. Okay. Cool. You guys all there? Everyone there? Cool. So now we're going to now take this that we just sort of learned about working out components of vectors and apply it now to systems in equilibrium. What's equilibrium?
When your resultant is 0.
Yeah, when your forces are all balanced and your resultant is 0. Okay. So now, if I'm going to draw now a system of vectors. Okay. I'm going to call this F1. I'm going to call that F2, and I'm going to call that, F3. Right? So what we can see now is, like you guys said now, when your resultant is 0, your forces are balanced and you are at a state of equilibrium. So if I work out this, my FR will be 0. What is an equilibrant?
The force that balances the other two.
Yeah, it's a force that will bring my entire system to equilibrium, right? So if I look at the system and I said, this system of forces is in equilibrium, F3 will be the equilibrant of F1 and F2, F2 will be the equilibrant of F3 and F1, F1 will be the equilibrant of F3 and F2. Does that make sense? That if I were to remove any one of these forces, my equilibrium state will be sort of no more. It'll be messed up. And if I replace that force again, I'll get back to equilibrium. Makes sense? So as I replace it, it brings me to equilibrium. It is therefore the equilibrant. Yes? Yes?
Yes.
Thank you. Okay. Cool. So now, on page 8, right, I want us to quickly try this together. We're going to first do the components, and then we're going to go do the example on equilibrium. Does anyone have any questions at this point?
No.
Not at all. Okay. So we're going to look at the worked example at the top of the page, number 1. Okay. It says a soccer player takes a penalty kick. He kicks the ball with a velocity of 10 meters per second towards the goal at an angle of 30 degrees from the ground. I'm going to try to use my super artistic skills to dazzle all you guys. I hope. That's a sort of goalpost there. We've got our soccer player here kicking a ball that way. Yes? So my vector here, it's velocity vector, 10 meters per second at an angle of 30 degrees from my horizontal. Yeah, everyone can see that, right? In their heads. World Cup, you're there. Okay, sweet. So now, as we do that, we can then, the question is, what will the ground velocity of the ball be? B, what speed will the ball gain height? Okay, so now again, think components. If the ball's going up that way, if you're looking from the top, you'll sort of see the ball going at a particular velocity. If you're looking at like, if I'm the goalkeeper, I'll see the ball just sort of rising at a particular velocity. That makes sense to everyone. Okay? And that's again, it's quite basic, quite simple. We look at our velocity vector, 10 meters per second that way, 30 degrees this way. We want to find our Fx, that's our ground velocity. We want to find our Fy, that's our rate at which it gains height. Yes? Yes? Yes. Thank you. Okay. So now, let's find our ground velocity. So our ground velocity is going to be our Fx, which is going to be our force, or our velocity in this case rather, times cos theta. That's going to be 10 times cos of 30, right? And what does that give us?
8,66.
8,66 meters per second. Yes? Okay, and then let's look at the rate at which it gains height. Fy is equal to our F times sine theta. That's 10 times sine of 30. Without a calculator, how much is that? 5, yes. That's 5 meters per second. Now again, I'm missing my direction here. For Fx, what's the direction for Fx?
Towards the goal.
Towards the goal, right? And what's my direction for Fy? Upwards. Yeah. Now just one for extra credit. Seeing that he kicked it at 10, but it only sort of approaches the goal at 8.66. If you wanted to get the ball in the goals at the fastest possible speed, what angle would you kick the ball with? 0 degrees, right? Because then you have all your force and all your velocity in one axis, and then it doesn't really sort of waste any of the velocity in any other direction. Okay, sweet. So I'm always advocate for bottom left, not top left. Cool. Yes?
When so it's kicked at 10 newtons, but then we're finding our velocity, which is obviously in meters per second, right? So does that?
It's kicked at a velocity of 10 meters per second.
Oh, sorry.
Yeah. So we're dealing with the velocity vectors here.
Okay.
So I just wrote F because it was the thing that the equation that I gave you, and it sort of makes sense. So we should actually just have the velocity in the x, and the velocity and the velocity in the y. Thanks for that. And we end up with that there. Is that better? Okay. Sweet. Now let's do the equilibrium question, right? So now if we look at the bottom of page 8, okay, it now says the worked example. We have the following forces acting on an object. We're gonna then have F1 at 20 newtons at a bearing of 60 degrees, F2 at 15 newtons at a bearing of 270 degrees, F3 at 10 newtons with a bearing of 200 degrees, F4 at 10 newtons with a bearing of 180 degrees. Find the components of F1 and F3. The B, calculate the magnitude and direction of the resultant of the system. C, calculate the magnitude and direction of the equilibrant in my system. Yeah? Okay, that's simple enough, right? Right.
Yeah.
Yeah, thank you. Okay. Cool. So now that's quite chilled. We're going to look at now, I'm going to draw these vectors up quickly. Okay, that's my point there. We have F1 at a bearing of 60 degrees, so F1 is sort of there. F1, that's 60 degrees from my sort of north point there. And that's 20 newtons. Okay, we have F2 at a bearing of 270, so that's that way. That's F2, which is 15 newtons. Okay, and then we have F3 at 200, so 200 is just beyond 180. Yeah, so that's there. F3, and that's 10 newtons. So bearing of 180, I've got 180 plus 20 to give me 200, so that's going to be 20 degrees in there. Yes? You guys with me?
Yeah.
Okay. And then F4 at a bearing of 180, so F4 goes perfectly down like that. F4 at a bearing of 180, and this is 10 newtons as well. Okay. Is everyone cool with this? Okay. What I like doing is finding all my angles that I'm going to use now for my, remember I need to find the angle between the x-axis and the vector itself. So for F1, 90 minus 60 is going to give me 30 degrees in that corner there. For F3, 90 minus 20 gives me 70 degrees here, and that's 90 degrees anyway, and that's 90 degrees anyway there. Happy? Yes?
I don't understand why the 60 is on the left side of the vector F1.
Remember, F1 is at a bearing of 60 degrees. So from my 0, my north, I'm going to go clockwise 60 degrees that way.
Isn't it 60 degrees from the horizontal?
No, it's a bearing. Bearing, you always start at the top, from your north, and you go clockwise around this way there.
Okay.
Cool. Is everyone with me? Thank you. Sweet. Now we just need to find our resultants. So now, the components of F1 and F3. Yes? So for F1, I'm gonna do this in sort of a table format. F1 up there, F3 down here, X component here, Y component there. Yes? So my X component, that's Fx is equal to F times cos theta, and in this case as well, Fx is equal to F times cos theta. If I'm writing too small at the back, please let me know.
Yeah, please write a little bit bigger.
Okay, cool. So trying to make good use of the space on the board. Is that better?
Yes.
And again here, Fx is equal to F times cos theta, and here Fy is equal to F times sine theta, and also here Fy is equal to F times sine theta. And then when we look at F1, our force is 20 newtons, our theta is 30. Agreed?
Yes.
Okay, so that's going to be now there 20 newtons times cos of 30. Okay, and does anyone have an answer for me? 17,32. 17,32 newtons direction. Direction of F1x. Remember, it's my x component. It's going to either be up, down, right, or left. Right. Okay, cool. And then the y component is going to be 20 times sine of 30. What's that going to give us? Quickly. 10. 10 newtons direction. F1y. Up. Okay. So remember, F1y is going there. It's going up and right. And F4 is purely down. F3 is down and left. F2 is purely left. Let's do this one quickly. For F3, we've got F3 is 10 newtons, right? Times the cos of, now our angle is 70 between the x-axis and the vector. You guys with me?
Yeah.
Okay. Cos 70. Anyone got an answer for that?
3,42.
3,42 newtons. What direction? Left. Okay. Fy, that's going to be now 10 times sine of 70. And that gives us anyone else have 9,39? Yeah, 9,39 newtons. Direction. Direction.
Down.
Downwards. Okay. So now as we look, all our vectors are now resolved into purely y and purely x. Where F2 is now to the left, F4 is down, F1 has its right and up, F3 has left and down. Okay? So we did the first part correctly. The next part, what we need to do? The magnitude and direction of the resultant of my system. That's chilled. So I'm just going to say fx, now this is my resultant of fx. So I'm going to add up all the x values. At this point, let me pick a sign convention. I'll pick my favorite. Right is positive, left is negative. Okay? So then let's start with the purely sort of horizontal ones. F2 is going to be 15, so we're going to have F2 there plus F1x plus F3x. And that will give us F2 is 15 in the left, it's going to be negative 15. F1x is 17.32 to the right. Left, that's going to be plus a negative 3,42. And does anyone have an answer for that one? Should give us 1,1 newtons to the left. Agreed?
Yeah.
Okay. And then you guys all see at the back still. Okay. Okay. I'll put it at the top there in the corner. Sweet. So let's find now our resultant in the y. Okay. So alright, Fy resultant is going to be now the y component of F1 y plus F4 is coming down, F4 plus the y component of F3 y. That's going to give us now F1y we have up there, which is 10 newtons upwards. In this case, I'm going to say up is positive and down is negative. So F1y is 10 newtons upwards plus F4 is 10 newtons downwards. That's a negative 10 plus F3 is F3y, sorry, is 9,39 newtons downwards. It's going to be negative 9,39 newtons. What's my answer for that one? 10 minus 10 just cancels, we left with negative 9,39. Which gives us 9,39 newtons downwards. Everyone still with me? Okay, can I erase this half of the board so we can do the next part?
Yes.
You.
Can you not erase the fx on?
Yeah, I'm going to leave these answers and I'm just going to erase this bit here. Okay. Okay, sorted. So we now have our resultant in the y, we have our resultant in the x. Let's just now find our total resultant. Okay? So now if I draw these vectors out, you notice I've got 9.39 newtons downwards, right? And I've got 1.1 newtons to the left. So that's going to be a little tiny vector up there like that. My resultant will be in this sort of direction there. Everyone with me? Hello?
Yes.
Thank you. Okay. So now we need to find our total resultant. Let's call that r. Using Pythagoras again, r squared is equal to, we're going to have our fx squared plus our fy squared. So r squared, our fx, we said, is that negative 1.1 squared plus our fy is that negative 9.39 squared. Okay? And then to find r, we need to just square root this and square root that, and we'll get differential answers. If you put that in your calculator, you should end up with 9.45 newtons. Give me a yay if you get the same answer.
Okay.
Okay, awesome. Now we just need to find our direction. Yes? So what I'm going to do is I'm going to put my theta there. Right? So with my theta there, I'm going to then work out my angles. Then tan theta is going to be now opposite over adjacent. So if I say tan theta is equal to my opposite over adjacent, that's going to be my fy over my fx, yes?
Yeah.
Okay, and then I can solve theta by doing the arctan of this whole thing here. So theta is going to be the inverse tan of my fy. What's my fy? 9.39. What's my fx? One negative. Sorry, they're both negative actually. Negative 1.1. And then what's my theta?
83.32.
80.
83.32.
Okay. 83.32 degrees. Is that my final answer?
No.
Not. Okay. How do I get my final answer? Let's use. Okay. So what do I do to get the bearing?
So you come from north.
I'm gonna have 0,
Yeah.
90, 180, 270 minus that theta there.
Yeah.
That makes sense to everyone? Okay. So for the absolute now bearing, it's going to be a bearing of 270 degrees minus 83.32 degrees. And what's my answer?
186.7.
186.7 degrees bearing. Does that make sense to everyone?
Yeah.
Any questions?
No.
Not? Okay, cool. So you guys have about 15 minutes to quickly go through several questions. If you have any questions at all, like I said, Dylan's over there, Robin's in the back, I'm over here. Give us a shout and we'll help you. So then what you can do is you can start all the way from page 6. There's a question on page 6. There is now on page 8 the number 2 question as well. Okay? And then the last one on equilibrium is going to be on page 9, the activity question. So if you cover all the activity questions up until page 9, then that'll be great. So cool. You have friends around you on the table. If you can work together, that's great. And if you need any extra help, again, like I said, please give me a shout, give Dylan a shout, give Robin a shout in the back, and we'll be with you. Cool. Let's push, guys. Can I raise the board now? Okay.
Sorry.
Yep. Yep. Sorry guys, I left that entire question. The last one we're doing, we had to work out number C, the equilibrant of the entire system. Sorry, okay. Now, if I've got the resultant, and I want to work out the equilibrant, right? So remember, if my resultant's one way, to bring me to equilibrium, I must just counter that resultant. So I have the exact same magnitude as my resultant in the exact opposite direction. So the easy thing about that is, so now let's call this now our FE, right? Our F equilibrant. It's going to have the same magnitude as my resultant. So it's going to be 9,where's our answer? 9,45 newtons. And then to get the direction, it must be in the opposite direction. So with our bearing, just minus 180 from that, and you'll get your answer. So then with this, it's going to be, the magnitude is 9,45 newtons. And for my direction, I'm going to say the direction of my resultant, 186,7 minus 180 degrees, and that'll give me 6,7 degrees bearing. Thanks for that, sir. Is everyone with me? Any questions?
How did you get the 9,45 newtons?
That's from our resultant. Remember, it's going to have the same magnitude as the resultant because it's got to counteract that and balance it out. Everyone else good? Okay, cool. Let's get started with those questions. Guys, the most important question that I want you guys to do is the one on page 9. So if you can start with the one on page 9 and then work your way backwards, that'd be perfect. But if you're struggling with page 9, go to the ones before and then work your way to page 9. Any questions?
No.
Was good, yeah? Yep. For the equilibrium. My resultant has a bearing of 186.7. So the equilibrium will be in the exact opposite direction.
that's